I am Adrian Wooten, one of the research scientists here at the South Central Cask. And can you just confirm for me that you're seeing the right screen? Just the slides, not presenter view? Okay.
Yes, that's good.
Good. Sometimes I end up sharing the wrong one. So ahead of what we're going to do today with this training activity, we're going to talk a little bit about the projections and what they are, how they're created, and a bit of a primer for everybody as we go into that activity, which Derek will talk about a little bit more in a moment. So first up, what are climate projections in general? So, according to the Intergovernmental Panel on Climate Change, there are two main definitions for what climate projections are. In general, they can be any description of the future climate and critically the pathway leading to it. But more specifically to what we're going to talk about today, they're model derived estimates of the future climate. And we'll get to that in a moment. Now, it would be lovely and ideal if there was only one set of projections to work with, like this particular example from Oklahoma City here, with just one projection. It would be a nice thing. It would make planning and decision making so much easier if there was only one to work with. And this is real data from our in-house projections here at the Cask for Oklahoma City. But the reality is we have a lot of projections to work with, and this is true for Oklahoma City as well as for anywhere else you might be working in the United States, that there's a lot of information now available from various data sets and sets of climate projections all across the country. And for those unfamiliar with working with them, I can totally understand if a reaction like this is what immediately comes to mind, and that it might be a lot of information to work with. But the next question we often get here at the casks about that is sort of the which one do I choose? Because there is sort of desire to just work with the best thing that there is and all that kind of jazz. But that's where it becomes a bit of a problem because asking somebody is not muted. Um, um, Working with a climate scientist and asking me which projection is the best is quite a bit like asking asking a car dealer which of the cars on here is the best and which one do you choose. And in such situation, both are going to ask, well, what do you need said car for? What do you need the projections for? Is what I'm going to be asking about in that particular case. The reality is there's lots of projections here, but which one you want to use or which ones you want to use, as it's advised to use more than one, is really going to depend upon the region you're interested in, the kinds of decisions you have to make, and the like. So there's a couple of different reasons why there are so many different projections, and that has to do with multiple aspects of how climate projections are produced that can result in different futures. Or to use IPCC language here, there's multiple pathways to future climate. The path taken by each projection depends upon a number of factors. Each of these are described in climate literature, but the first of these is a question on, well, human or societal actions. Okay, how much in emissions, how much in development, and things like that. Those particular emissions scenarios that define societal action are then passed along to the global climate models, which give us a sense of the scientific side of things, how the climate would respond to changes based upon the forcing or the force on the climate from those particular emissions scenarios. There's also the third aspect, because of course we want to understand what does climate change mean for things happening locally. And so there's a third aspect that's called downscaling, which translates the information from the global climate models to local changes. And so if you're following along, we have emission scenarios for human societal action, and there's multiple of those. There's multiple global climate models to work with, each of them taking each one of those emission scenarios. And then there's also multiple ways to translate global information to local scales, and hence the reason you can see pretty quickly it balloons out very fast. So for our example with Oklahoma City, as a way to think of it, you can have those projections here based upon emission scenarios just as a start now instead in Oklahoma City. And what we have here is one example for each of the three emission scenarios, or in our case, what they might be referred to is as RCPs. The second component of those projections, as we talked about a second ago is the global climate models themselves. And when we're talking about climate, just specifically, we're talking about a lot about physics. All of those equations there, for example, are prime things that are included in the climate models, but put into forms where they can be solved by computers. The kinds of models we're referring to, of course, are global climate models, which by their name are run globally here. But what's important to remember with the global models is they're not trying to predict the weather on a given day. Instead, what we're interested in is to understand how the weather on average will change given some changes in external forcing. For example, if you double the amount of CO2 in the atmosphere, what would happen? In essence, the climate models give us a sense of how the climate at large would respond to a given emission scenario. So hence again, emission scenarios, global models, and then we'll get to the third component. The thing is, there's actually a lot of those different climate models available. This map actually shows different modeling centers across the world that have produced global climate models for the Intergovernmental Panel on Climate Change reports. And then they also get used in subsequent assessments of impacts all around the world. Each of those global climate models and provided, there's more than 40 of them in one group, and the most recent generation, there's more than 100 of them. But why so many is a good question. Every GCM, just to emphasize it, every global model or GCM is based on the same fundamental physics. But there are some processes in the climate that aren't fully understood yet. And as such, there are some competing theories for how they can work and different equations that represent those theories and result getting incorporated into different models. One example of this, just to take as a toy example here, is cloud formation. So let's suppose here that the scientist on the left comes up with a ratio relationship between temperature and cloud formation based upon his or her research here. And then suppose you have it a couple of years later that another scientist in their postdocs comes up with a slightly different relationship based on their research. Each relationship may end up being in a different climate model, and there are different competing theories for how a cloud could form. Now, again, obviously, this is a very toy example just to make the point of how this can happen. And there's obviously more than two competing theories for some of these processes. But just to make the point here that you can have these competing theories for a simple process that can end up resulting in different equations for how they're represented and end up in different models. Now, I do want to emphasize again here, the fundamental physics are exactly the same between the different global models. The major differences arrive in just the representations of those phenomena that we don't have a complete understanding of as yet. Cloud formation isn't the only process where this is the case, too. There's actually several of them in this particular graphic where you can actually have multiple equations and multiple theories for how that particular process works in the atmosphere. And also atmosphere to ocean and ocean to ice and the like. For that reason, because we have multiple global models that can each take the same emission scenario to run and provide information on how the climate may respond, we can end up with more projections of the future climate. Or in the case of OKC, as you can see in here, end up with more projections of the future climate, more lines that get added onto the graphic. So we've got emission scenarios and then multiple models run with one particular emission scenario. The final component, which I mentioned before, is something called downscaling, which translates global information to local scales. So first thing I'm going to do is explain real quick why downscaling is used at all with an example from Puerto Rico. So the map on the left here is a satellite image from Google Earth for the island of Puerto Rico, overlaid with the lines that represent the boundaries of each grid box of a global model, because these are models that are run on a grid across the whole world. So the way you can think of it here is you have one number per each of these grid boxes. This is problematic for Puerto Rico in their decision-making with regard to ecosystems and planning and infrastructure and the like, because Puerto Rico, being quite a small island, is also very mountainous, as it were, and it transitions very quickly from coast to mountains. The result of this is results in a very sharp gradient in temperatures and precipitations over very short distances. And the reason it's problematic then to use just a global models information for Puerto Rico is because all of that variability is captured in one number in the GCM. even though that will not change, that particular variability will not change as you go into the future. Downscaling is designed to incorporate the influence of topography, proximity to the oceans, and much more that cannot be accounted for in a global model because of computational limits on just how fine those global models can run, how small those grid boxes over here can be. Excuse me, um, without breaking a supercomputer, if you will. And so that's what downscaling is there for. It's designed to increase the resolution or shrink the size of those particular grid boxes in a global model. But it's also helps us to answer our stakeholders' questions here at the CASC about how climate will change in their particular location for impact assessments and better represent local features. You can see this as a good example actually with the Rocky Mountains here in this image, where this is reduced to a much increased resolution rather. It's a smaller set of grid boxes here compared to what it is in the actual global model results. Now, for much the same reason as we have with the global models, we have multiple different downscaling techniques. We're still investigating different ways and the most appropriate ways to do those translations from global to local scale. So as such, you can have multiple emission scenarios run with each of the different multiple climate models, and then multiple downscaling techniques on top of it. And as a result, the number of lines here with the projections grows pretty dramatically. If we put all of that together, we come back to Oklahoma City again, you can see it pretty clearly that the projections grow out in number pretty quickly just because of the number of global models that are used, the number of mission scenarios that are used, and the number of downscaling techniques that are used. Now, the CASC makes use of, the CASC has to, and the other boundary organizations addresses this a lot, along with our different different partner agencies around the region. And so if you're going to be ending up using the climate projections in your work or in of your adaptation planning and things like that, that's some of the things that we are here to help with in helping determine which groups of climate projections are most useful, what the projections suggest would happen for the area, for the system that is of interest, as well as, you know, how well can we trust certain things, what can or can't we trust about them, what are the caveats that are important, and the impacts some of these changes might have on the system of interest, working together with others and with yourselves. A lot of these answers are pretty unique to what the application is and what some of the interests are in here. And that's actually one of the reasons we designed this particular training activity that gets into a quasi real world decision, because that's where it's going to be your turn to be working with some of the projections to make a quasi real world decision.